Hello, Tensor friends. I got called out on one of my videos because I just did something without explaining it, and I really appreciate it when you guys call me out. It makes me better at this. I really do appreciate it. I was doing a derivation of the divergence in cylindrical coordinates, and the first thing I wanted to do was derive the del operator in cylindrical the coordinates. So I said, "Oh, how would you express the gradient as a tensor?" And I wrote this down. And then I immediately said, well, it's obvious that, I don't know if I said obvious or not, but that's what I intended, is equal to this. And they said, well, what, WTF, dude? Why is that? That's not obvious. And you're right, it's not obvious. I'm sorry. So let's do it. Okay. So I'm just going to take this part and this part, right? So we're saying the gradient of a scalar function or scalar field, a scalar, is equal to the contravariant derivative times that scalar, the function, times the covariant basis of the vector, okay? So this here can be expressed like this. This contravariant del operator can be expressed as the contravariant metric tensor times the covariant del operator, right? So all I'm doing is raising the index. And we've done this before. You can raise and lower indexes using the metric tensor, right? So the step I skipped, I should have said, okay, here's what we got. And when you see an operator next to a letter, a variable like this, it implies there's a parenthesis there. So all I did was I substituted that in and I didn't make it specific what I was doing. All right. So I put this in for that right here. And then I took this jump of saying the covariant derivative of a scalar is just the partial derivative. It's like, what? Is that? Why is that? Okay. The definition of a covariant derivative for a vector is this, right? And we've done this before too. The covariant derivative of a contravariant vector is equal to this times the Christoffel, the symbol, plus the normal directional derivative. Now, in Cartesian, the space, the covariant derivative and the directional derivative are the same because there are no Christoffel, the symbols, right? They're all zero. But that's not true in other places, in other spaces, right? So the reason the covariant derivative was needed was because the basis vectors in curvilinear coordinates, the system changes everywhere in the manifold. So if you just take this directional derivative without worrying about the basis of vectors, you're not going to get the right answer. So that's actually why this was derived to start with. Well, what are we dealing with here? That's a scalar field or a scalar the function, either one, it doesn't matter. So scalar functions, scalar fields have no basis vectors. They are tensor rank 0. Thus, the covariant derivative and the partial derivative are the same thing. Because if you don't have any basis vectors, you can't have this. Because these are made up of the metric, the tensor. And if you have no basis vectors, you have no metric tensor. So this is 0 for a scalar field, right? So that's just what I implied, and I should have explained why is that the same as this, and I didn't. I'm sorry. Hope that clears it up. Thanks for watching. See you later.